Hey there, and welcome to the last lecture in this module about seismic attribute analysis. So we're going to wrap up just talking really quickly about some of the ways that we can combine multiple attributes at once and integrate them to help with our interpretation. So there's a lot of different tools that are available to us. In this mini lecture, I'm going to focus on those related to visual decision making, but in later lectures, in different modules, I'll talk about projection techniques such as principal component analysis and independent component analysis. There's also statistical analyses that can be done from ANOVA to Kriging, multilinear regression. And then we have our machine learning multi-attribute analyses. And so this includes things like k-means, Gaussian mixture models, self-organizing maps, and then supervised learning methods from probabilistic neural networks to random forest, generative adversarial networks. And so a lot of these I'll talk about in a later module for this course. Okay, so focusing this time on visual decision making, I'm going to talk about cross-correlation maps first. And so these are one of the simplest ways we've been doing it, probably, for many decades. You've probably been doing it as a seismic interpreter yourself. And so this is just taking the seismic attribute and comparing it to perhaps a well that you have or some information that you have to validate the seismic attribute, and then taking that information and applying it to another case. So in this case, we've got our seismic amplitude data, and we're looking at it around the Miller well marked in white, which was a productive well. And we're looking now across the area of interest where they're perhaps going to plan a well, the Wintershaw well, to try to see if there's any correlation between production, as we have around the Miller well, which is redder and kind of in colors in terms of amplitude. And we notice that those amplitudes aren't quite as high around the Wintershaw well. And so that's telling us that perhaps there's a difference in rock properties or fluid properties between these two areas, the productive well and then the proposed well. So nice, simple method. Co-rendering is another very simple method. This is where we take different attributes, we render them in different colors, and then combine them together. And so you've seen lots of examples throughout my lectures using like a gray scale and a rainbow scale where I've combined them together. In this case, I'm showing a quick example where we're taking 3 different attributes and we're putting them in to 3 different colors. So we've got the yellow. So one attribute is shown in yellow, another one in magenta, and another one in cyan. And so we've picked out our attributes so they kind of align with some of the features we want to pick out geologically, from flexures to sharp faults, like coherence, and then amplitude change. And when you combine all 3 of those together in one volume, like this image here on the right-hand side, you're able to kind of combine those insights from the 3 different attributes into one visualization. So it really helps us with combining all that is known. So we've got not only the sharper, clearer, larger scale discontinuities, which are probably faults, to seeing some of the subtle areas that may be fractured. Okay, so then this is also done in like a red, green, blue is another way that you often see these combined. So here with co-rendering, we are going to show an example of combining coherence, and here with most negative curvature. And so I'm going to show you right now, we've got one in grayscale, where our coherence is highlighting the lateral discontinuities. And then we can put in our most negative curvature, which is in that kind of red, white, blue scale. And we can combine these together in order to see the synclinal features, but then also some of the discontinuities. So now they're blended together. And so this is another way to visually integrate multiple attributes in a co-rendering type technique. Let's see, we could also kind of do some interactive clustering using visualizations. So in this case, we kind of have the coherence where we could see the channel edges, And then with the curvature, we were able to see areas where we have more compaction, so the synclinal features, which then at the kind of confluence of the two of them, we understand where the channels are perhaps more shale filled. Here's another example using more of a chair display where we can see the vertical and the time slices. And as I kind of go through this, you can see in this case, we've got the coherence, the most positive, and the most negative curvature. And when we blend them together, we get a very interesting visualization that's showing us some information about differential compaction, which is, as we know, is a lithologic indicator, where the most positive features are suggesting more of a sand-filled channel, and the more negative features indicate shale-filled channels. And so then we can go between the two of them, and we can pick out our channel systems and then understand which ones are perhaps more shale-filled and which ones are more sand-filled. All right, and so in another case, what I'm going to show you next is we're putting together attributes that give us a ridge shape, so an area where we have less compaction, and then with our channel edges, and understand which ones are sand-filled. And so here's a case where we have our coherence, and we're going to co-render it with our bowl component. So this is kind of a longer wavelength curvature. We call them shape indices. So we've got bowls, we've got ridges, we've got valley shapes. There's a lot you can pick out by combining different aspects of your curvature. And so what we're showing here is our bowl shape indices, kind of mapped in blue, with our coherence, overlying our coherence. And so when we look at it with the vertical section next to it, we can see how that bowl shape kind of relates to those compaction features. And we can do some kind of transparency methods depending on the software that you have available to you to really show them. All right, and then, and so that kind of showed us the karst aspects, where we might interpret from those bowl shapes where we have those karsting features. Okay, so the next one is spreadsheets. And so this is just kind of more maybe of an old school way, but it's very common in exploration risk analyses. And so this is a quick example where we're using the attributes and correlating them to the underlying geology. So this is an example from a few years ago where the authors had a 3-component 3D survey, and they generated a whole bunch of attributes, so a suite of attributes that were sensitive to fractures, from coherence to curvature, the AVAZ P wave, anisotropy, shear wave splitting, so a lot of different attributes. And then they combined them in a risk analysis spreadsheet and used a model-based decision tree as their analysis tool. And so the result is that where you have multiple attributes, so kind of showing down here on the bottom of the right-hand side. And so you can highlight the areas where all of those attributes are giving you a high probability of fractures. So it's kind of like the yellow and the red areas down here. So you're taking the information from the spreadsheet where all the attributes tell you have high probability of fractures, and then you're mapping that onto your seismic. And so this is kind of that multi-attribute fracture prediction that you can use with the aid of using a spreadsheet. Okay, next one is cross-plotting and geobodies. So again, very standard, well-known techniques. Here we've got an example of some scatter plots that are created looking at the 8 Hertz and then the 20 Hertz component. So we've done a spectral decomposition of our areas, and the brighter areas in this cross plot show you where you have a larger number of spectral pairs that have the same frequency. So areas where you have the same spectral frequency between the 8 and the 20 Hertz. You can then kind of do, if you have access to an interactive clustering software, you can highlight the ones that you're interested in. So in this case, the user highlighted those kind of shown in this orange box and displayed them back onto the seismic data. So this is kind of using your geologic knowledge to create your interpreter-defined kind of cluster. And so in this case, it's a fairly laterally continuous region that we're seeing on the 8 Hertz data. You can also use cross-plotting as a multi-attribute analysis tool, where you can use it to define your geobodies in the software package. So in this case, they've highlighted here areas of lower coherence in this case. So this is the Fort Worth Basin in Texas, and we're cross-plotting the coherence with the most negative curvature. And then this yellow polygon is an area that was selected because it was more anomalous based on the knowledge that the specific interpreter had. And so it highlights the voxels in the 3D seismic, kind of using that geoprobe, geobody technique, where they exhibit both the characteristics that are kind of anomalous with coherence and curvature. Okay, another way you could use a crossplot is to analyze lambda rho, mu rho to estimate your mineralogy. So here we've got some vertical slices of the lambda rho up here, and then mu rho on the top right, and in the bottom left-hand side we have the crossplot. And so between lambda rho and mu rho, we know what regions we would expect clay in, where we would have the more quartz-rich lithologies and the more limestone-rich lithologies. And so we can map those using in this color scale. We can map those back into our vertical section in order to understand which areas may be more quartz-rich, which areas may be more limestone-rich or have clay. So they're all very useful in terms of estimating the mineralogy in your region of interest. And then here's another example to that too, now showing it more in a straddle slice rather than a vertical section, but doing the exact same thing, where we had previously the lambda rho, mu rho, and now we're looking at, okay, so what's the mineralogy in the Marble Falls limestone? Okay, we can see the areas that are more clay rich in the green, the areas that are more calcite rich in the pink. We've got the upper Barnett Shale, and we can see that that is very clay rich for the most part, but we can see where there's heterogeneities within the upper Barnett. And then a few other formations from the Forestburg limestone to the lower Barnett, which is a more kind of quartz-rich clay, it looks like, in the Viola limestone. And so you can hopefully see how that co-rendering of lambda rho, mu rho gives you information about mineralogy. Okay, and then the last one I wanted to mention was connected component labeling. And so this is where we go in and we can label the features that we're interested in. And so here we're doing some body labeling of the karst features using the attributes that we picked out. And you can see we've got kind of like a spectral decomposition going on here. And so this is kind of interesting because this data set had been worked on for like a decade before this method was applied, but by using this connected component labeling, it was the first time they were able to fully delineate the connectivity of the karst bodies in the seismic. Here's a case where we're co-rendering and using opacity for geobody detection. And so in this case, there's a few steps you have to go through to be able to use this type of visualization. So first, you need to co-render the attributes in your zone of interest, and then draw a polygon where your region of interest is. And so you can see it's marked right down here. And then you interpolate the different colors with the polygon using a kind of diffusion operator to interpolate, and then set all the colors in the polygon to be opaque and all the rest are transparent. And so I'll show you what that does when you go through this. All right, so there's our polygon. We've set everything else to be transparent. And so now we can see regions in the seismic where it is similar to our region of interest. And then from that, you can move into 2D and 3D. So in this case, we're looking at 3D, where we can see from the spectral component analysis all the geobodies that were similar in the seismic in our different multiple attributes to the area that we're interested in, using that opacity. We can then go through and we can pick out different, and here we've got the RGB spectral component that we were originally working on. We can look at the envelope. We can do the same thing in that case where we're kind of thresholding or picking out the amplitudes that were similar based on amplitude, based on the envelope also, to really see and pick out geobodies of interest to us. Okay, so just to wrap up, like a quick summary of those techniques, you want to keep in mind that when you combine attributes, you get a lot more information out of your data. So combining the attributes gives you more information than any single attribute alone. So you can do this through simple clustering. You can do it through co-rendering, through color blending. I showed you the example of opacity. And then there's a lot of modern tools out there, and I know everybody uses different seismic software packages, but most of them have ways where you can do the transparency. You can have access to cross-plotting tools, which become very valuable when you also have well log information. And then the interactive clustering is really important. So that's where we as our interpreters can choose the way we're clustering. Maybe we have knowledge about production that we want to wrap into our attribute analysis. And so it's a great kind of first step when we're doing quantitative analyses. So thank you very much for listening.